Okay, good afternoon, everyone. Thank you for joining. We are right at the top of the hour. Welcome to the Safer Sim webinar series. My name is Jacob Hayden, and I'm a program coordinator for Safer Sim at the University of Iowa. Safer Sim, or Safer Safety Research Using Simulation, is a Tier 1 university transportation center with the research priority of promoting safety, and our webinar series features the research projects from within our center. So thanks for joining us today. We will have time at the end of the presentation for questions and discussion. So attendees, feel free to use your microphone or the chat box to participate, and feel free to use the chat box at any time throughout the presentation as well. And we will hold those questions and address those at the end during the Q&A. I will also say this webinar is being recorded and will be shared online afterwards. And with that, today's presentation features a project from the University of Iowa. I'm pleased to welcome our presenter, Jeehan Malik. Jeehan, I'll turn it over to you.
Thank you. Hello, everyone. My name is Jeehan, and I work at the Hank Virtual Environments Lab at the University of Iowa. And today I will be presenting our work where we looked at whether simulated augmented reality overlays influence street crossing decisions for non-mobility impaired older and younger adults. So the reason we are doing this work is because functional declines because of aging can cause cognitive, perceptual, and motor declines that can hinder older adults' ability to perform their daily life activities. And research has shown that two areas where older adults face particular challenges are independent travel and transport. And stats have shown that older pedestrians are more likely than younger to get into fatal road accidents because they're more prone to sustain injuries and get into medical complications. And so with this context, and given that vehicle technologies are growing at a rapid pace, and connected vehicles technology will enable vehicles to communicate with other vehicles, infrastructure, and also pedestrians, some technologies here that can help older adults with safer street crossing are smartphone devices and emerging technologies like augmented reality. So we examined the impact of both of these technologies on pedestrian street crossing behavior. And our prior work looked at smartphones, and we used those findings to now look at how augmented reality overlays would impact pedestrian behavior. So before getting into these, I will go over how we conducted the studies. So we have a large screen cave simulator set up at our lab. And that's basically like a 3-wall room and that participants can walk through. And they wear a helmet with reflective markers on it. And we track the position through these markers using the Motive OptiTrack motion capture system. And within these screens here, we project high resolution graphics of an urban neighborhood onto the screens. And our scenario basically looks like a 1-lane road with traffic, a continuous stream of cars. They're approaching the participant from their left-hand side towards the right. And the gaps in between the cars range between 2 to 7 seconds. And so we have participants choose whenever they feel that it is safe, they can just walk across this room and then walk back and then begin the next trial. And we have participants do 20 trials. And before that, we have 2 practice trials as well. And so participants just basically walk on the side of the roadway and then they can cross whenever they want. So I will now go over our prior work where we looked at smartphone alerts and warnings. So I'll briefly describe that work. So for that study, we had 3 conditions: control, where we did not display any alerts and warnings, and participants just crossed the road with a phone in their hand. And then we had our permissive condition, where we displayed permissive alerts that told participants when it was safe to cross. And then we had a prohibitive condition where we told participants, where the smartphone told participants when it was not safe to cross. And from this study, we basically found that it is especially difficult to provide effective prohibitive warnings because it's difficult to sometimes effectively align the approaching gaps with each alert or warning. So we found that visually participants had trouble mapping which alert or warning corresponded to which gap, and that this was particularly noticeable for prohibitive warnings. And we also found that participants could be less attentive to the road because they now had to focus on two different information spaces. So one was the virtual scenario around them, and then one was the information that they were receiving through the cell phone. And this divided attention could also impact their road crossing. And so because of these reasons, we then ran a study with augmented reality overlays within the same environment where each gap corresponded to a cue, which we called red circles and green arrows, which told participants whether or not it is safe to cross that particular gap. So we augmented, like, it was the same scenario where there was a one-lane road and traffic approaching the participants from the left. And we augmented these red circles and green arrows that indicated the crossability of a particular gap. So I will now go over our study design. We had two conditions for this study. One was the control, where we did not show any augmented reality overlays, and participants just crossed as whenever they wanted, with cars approaching from their left side. And then we had a combined condition where it was the same environment, but now we had red circles and green arrows within the environment, hovering above the cars. And we recruited 48 younger adults with ages between 18 to 26 years and 48 older adults with ages between 66 to 84 years. And we conducted a between subject study with both age groups of participants. And we recorded for each trial that the participant took, our measures were basically the gap chosen by the participant, the timing of entry of the participant into the roadway, and then the road crossing time, which was the time it took for the participant to enter, the time between when the participant entered the roadway and exited the roadway. So the time it took them to cross the road. And then time to spare, which was the time that they had remaining after they had exited the path of the roadway. And in addition to this, we also had checked whether or not participants complied with our overlays. So here we had two different types of compliance measures where we calculated errors of omission, which is the number of times participants chose not to cross a gap when a green arrow was shown. And then we had errors of commission, which was the number of times participants crossed when a red circle was there. So errors of omission are basically missed opportunities to cross, while errors of commission are like, they're more important because that's when participants crossed when a red circle was displayed and they were told not to. So this may have safety consequences in the real world. And so in addition to these measures, we also had NASA TLX scores. NASA TLX is a questionnaire that assesses the workload of a particular task. It has scales that measure mental demand, physical demand, temporal demand, performance, and effort and frustration of the task that the participant has to rate. And then we had additional ratings from the participants on scales between 1 to 5 of distraction, comfort, likeliness to use, again, in different settings. So similar settings, familiar settings, unknown settings, or large city settings. And finally, we also had qualitative data through interviews in which we asked participants about whether or not they found the overlays helpful, any issues that they had with them, and any improvements that they would suggest. So I will now start discussing our results. So we found that overall, older adults tended to select larger gaps to cross than younger adults. And these graphs here, they show their logistic regression graphs that show the probability of taking a gap with the gap sizes in the x-axis. And the right graph is for older adults and the left graph is for younger adults. So here we see that participants in the augmented reality condition, they selected larger gaps than participants in the control condition across both age groups. And also participants in the augmented reality condition were more discriminating in their gap choices. So they're accepting fewer of the smaller gaps and more of the larger gaps in both age groups. And so moving on to our compliance results. So most of the gaps that were chosen to cross by both older and younger adults were ones where a green arrow was shown. And so there were few missed opportunities to cross. And most of the gaps where a red circle was shown were not crossed by participants, which can be seen in this table here. And there were a few errors of commission. So to examine this further, we also assessed hypothetical errors of commission had the AR system been activated when participants in the control condition crossed the road. So we used the data from the control condition and looked at the gaps where a red circle would have been shown if this was an AR condition, and we looked at how many gaps were crossed by participants when a red circles would have been shown. And so here we actually found that the errors of commission would have been much higher. So in the control condition, participants took gaps, many more gaps where we would have displayed a red circle in the AR condition. So this indicates that the AR system actually shifted participants' behavior towards safer gaps. And then we also had our interval responses. So here we found that older participants in the augmented reality condition had significantly lower ratings for perceived mental and physical demand compared to older adults in the control condition. And we also found that in the augmented reality condition, the temporal demand scores differed significantly between older and younger adults. So older adults in the AR condition versus younger adults in the AR condition. And we did not find any other significant differences. And then for some of our qualitative results are shown here. So we found that overall, most of our participants found the overlays to be helpful, especially the green arrows. And then older adults participants, like their responses indicated that the symbols made the crossing task cognitively easier, and it was easier for them to visually align the augmented reality overlays with the approaching gaps. And this also matched our NASA TLX results. And then we found that both older and younger participants, they spoke to the symbols, making them feel safe. So for example, one older participant said about the green arrows that I just felt it would be a safe time to go. And then we found that most participants thought that they could trust the augmented reality overlays. And this was also concerning because some participants were implying that they were trusting the overlays without using their own judgment. And so this is something that we should be wary of when we're designing such systems. And lastly, we found that many more younger participants than older spoke about the red circles as being incorrect. Like basically they said that the red circles told them to cross when they told them not to cross when they thought they could. So for example, one younger participant said that I felt like they lied to me sometimes, like I could have crossed. So this concludes our results. I will now go over some of our discussion points. So overall, we found that augmented reality overlays made it easier to visually map each gap to a queue. So because we had these augmented reality overlays and they visually marked the crossability of each gap, so this visual indication made it easier for participants to kind of see when they should be crossing and easier to link the gaps with the approaching symbols. And then we also found that augmented reality overlays significantly reduced the physical and mental demand for older adults, which is promising because this means that augmented reality really did solve this problem of divided attention for older adults. And then we found that older adults were more cautious than younger adults across both our conditions, and they were more cautious. And other than this, we also have some considerations for augmented reality applications for people who design such applications. So we found that the size and clarity of the overlays is important, and positioning the overlays in a way that is understandable to users is also important, because augmented reality can also bring about an additional perceptual load. And so if it's not designed properly, it may increase that perceptual load, the amount of things in the environment that users have to perceive. And so there should be this balance of reducing the cognitive load and the divided attention, but also making sure that the perceptual load doesn't increase too much. And then designers of augmented reality applications should also be wary of user dependence on the overlays. So I talked about how participants mentioned that they were trusting these alerts, like the overlays, without using their own judgment, and they started relying on them, which is something that we should take into consideration. And so for future work, we are actually want to explore the implications of augmented reality further in more complex settings. Because we had participants say that they would be more likely to use them in more complex or settings that were not familiar. So such as like in multi-lane street crossing, which is more complex, or in other environments like large cities or unfamiliar environments for participants. So this concludes my presentation. Thank you so much for listening, and I will now be happy to take questions.